I will start the recording. Now I have to go find my PowerPoint. Oh, there it is. Okay, so we are starting with chapter 3, and the actual beginning of this class officially is chapter 10, but I wanted us to go over chapter 3 because it kind of eases us into chapter 10. So we'll go over chapter 3, we'll go over chapter 4, and chapter 3 covers the types of bonding we'll be seeing over and over again in chapter 10 and onwards. Chapter 4 talks about the type of intermolecular forces that we'll be seeing in chapter 10. So it's important for us to cover that so we don't jump into the deep end, okay? So chapter 3, once again, I took a bunch of stuff out just focusing on the types of bonding. We're looking at ionic and covalent bonding. If you have taken 1405, you have seen ionic and covalent compounds and the different kinds of bonding. So we are talking about bonding first. We're going to introduce that. What exactly is bonding as far as chemistry is concerned? When we're talking about bonding, we're talking about joining of two atoms in a stable arrangement. This is a very generic definition, right? But when we're looking at bonding, we're starting from that point of view, a very generic position, which is you have to have a minimum of two atoms and they are joining in such a way that they're forming a stable arrangement. So they go from being unstable before they bond to being stable when they bond. Okay, so the goal of bonding is stability. Okay, we're told that only the noble gases in group 8A do not readily react to form bonds. The noble gases in group 8A. So for this part here, you have to have your periodic table. Let me see. I'm trying to look up my busy background on my screen. I won't even try to mess with that right now. But if you look at the periodic table and look at the column far to the right, that will be group 8. Those elements in that group are already stable. They're already here. So they don't need to bond to become stable, right? Because they're already at stability. So for them, if you want them to bond, you have to use a lot of energy to force them to bond because the purpose of bonding is to achieve stability. Okay, and it says right here, because the electronic configuration is especially stable, they're already at the goal, which was stability. Now we're going into more details. Exactly how do these elements bond? We're told that three possible things can happen. Elements can either gain, they can lose, or share electrons to attain the electronic configuration of the noble gas closest to them in the periodic table. So all that is just saying elements start, they start as unstable. So I'll just say start with instability. So they're unstable. You know, you start as stable and you have to commit to it, right? So they're starting at a point where they're unstable. So they gain stability by, so they either gain electrons, lose electrons, or share electrons. Okay? And what was the ultimate goal of this? Once again, goal is stability. And how do they gain stability? We're told here, we're told in more details, they gain stability when they have the electronic configuration of the noble gas closest to them in the periodic table. So when they're being stable, if you look at the electronic configuration, it looks just like the ones that are in group A. So it would be like their goal is to be like the elements in group 8A. Okay? So now we're going to be looking at ionic and covalent bonding, and we'll come back and look at this illustrated again. One of your assignments in your lab is identify ionic and covalent compounds. Well, for that, you will actually have to look at the characteristics of ionic bonds. what type of elements come together to form ionic bonds? We're told here we have two types of bonding. Ionic bonds result from the transfer of electrons from one element to another. They haven't said what elements yet. I'm just going to go ahead and jump into that because I feel like it's taking too long to get to the point. Okay? With ionic bonds, we mostly see it's mostly elements, mostly the metal elements. So I'll say here metals and nonmetals. So I can confidently say that 95% of ionic compounds are metals and nonmetals combined together. For the most part, when you see ionic compound or ionic bonds being formed, so ionic, either bonds or compounds, we see the metal first, okay, and then the nonmetal second. So many times when you're asked, is this compound an ionic compound or does it form an ionic bond? Your eyes should rush to the first element and you're making a judgment based on its identity. Do you recognize the symbol? So look at the symbol and ask yourself, is the symbol given to you the letters? Do those represent a metal? If they do, then the first requirement is met for the second one. Do those symbol of the second one represent a nonmetal? And if the answer is yes, then metal, nonmetal produce ionic bond. Okay? And then we're told here the actual formation of the ionic bond results from the transfer of electrons from one element to another. Okay, once again, if this sounds like deja vu and you've done this before, hang in there. Remember, this is a warm up, right? This is when we're stretching, we're doing stuff. It's about to get real when we get to chapter 4 and then chapter 10. You see how different this changes, okay? Okay, so metals, nonmetal. Let me give you guys an example. I will use, for my ionic bond, I will use the common one. This is my go-to when I was in school, okay? Sodium chloride. Okay, so in sodium chloride here, we're seeing a transfer of electron causes a bond to happen. Once again, sodium here is our metal, sodium metal, and then chlorine is our non-metal. So how do these come together? First of all, when they're elements, we have sodium, metal, and then you have chlorine gas, okay? So we're told here that there's a transfer of electrons from one to the other, okay? So in general, we learned that metals tend to lose electrons. Okay, so this is kind of a review. If you've had chemistry before, you've learned this before. Metals tend to lose electrons. It has to do with their size. Metals are very, very big, and the electrons they lose are the ones that are further out. So I'm going to draw a sodium, huge sodium out here. The valence electrons, the outermost electron is the one that's being lost. And then the non-metal are right here, non-metal gain electrons. So how can we use the size of the nonmetal to justify why it gains electrons? Okay. By the way, I drew chlorine here as diatomic because in nature, chlorine is diatomic. Okay. So just in case you're wondering about that, when chlorine is by itself, it's diatomic. So real quick, I'm already starting to detour right here, right? I'm going to write it on the side here that for your diatomic elements, these are diatomic elements. What do we have here? Brin, coal, Hoff. If you've forgotten that, this is your chance to relearn that. Remember, bromine by itself, iodine by itself, nitrogen by itself, chlorine by itself, hydrogen by itself, oxygen and fluorine. When these are by themselves, we always write them as a molecule. They exist in pairs by themselves. The pairs separate right before they react, okay? But when I'm talking about the chlorine atom, I'm going to deal with just one right here. So the chlorine compared to the sodium is very tiny, and chlorine is actually surrounded by 7 electrons. So I've got 1, 2, 3, 4, 5, 6, 7, okay? So Because chlorine only has one outer electron, chlorine will lose the one electron to become, sorry, sodium will lose the one electron to become sodium positive, right? And this just says sodium lost one electron, okay? And then remember right here, chlorine had 7 electrons to begin with, right? So remember sodium had 1 electron. So right here, sodium has 1 valence electron. And then right here, chlorine has 7 valence electrons. Okay, so when sodium loses the 1 electron, guess who takes it? Chlorine takes in the electron from sodium. Okay, yeah, chlorine takes the electron from sodium. So what happens here is the chlorine takes the electron. So the question is, why is the electron drawn to chlorine? It has to do with the size of chlorine. Chlorine has a nucleus that's very large, not large in size, but that has a strong positive charge. That strong positive charge acts like a positive charge does, right? Like a magnet of negative electrons. So it keeps the whole atom small. It's kind of like it has this suctioning power that keeps the atom overall small. Remember, the whole atom is essentially a bunch of electrons, right? So this strong nucleus, the strong core, is pulling in all the electrons in chlorine, keeping it small, but it doesn't just pull on the electrons from chlorine. It will take in any other electrons that are free around. So when sodium loses a 1 electron, it gets taken by that tiny chlorine right there. So in the end, what do we have? We end up with a sodium that's positive because it lost the electron, and then chlorine is negative. This negative here is the electron gained. Okay, so very, very small atoms have the ability to take electrons from large atoms, right? Because the large atoms freely give up the electron. Then there's a whole chemistry that goes behind that. We can talk about 1405, but I won't go into the details. So sodium loses the electron, chlorine gains the electron, so electron lost and electron gained. Okay, are they stable? Technically, both of these are stable, right? How are they stable? When sodium loses 1 electron, it now gains configuration of noble gas element. Okay, so the question is, how can we justify that? I mean, I can just say a bunch of stuff. How can we justify that here? Okay, so I see that they're kind of going to what I'm going to right now. I want to just show this real quick. So what I'm going to do here is, let's see, can I pull up a periodic table? Let me see if I can find period, or if I can spell periodic table of elements. Let me pull that up and see. It's really difficult to find nice periodic tables. It's difficult to find free stuff online. People have just taken all the free stuff online and hidden them. So now you have to pay money to access what somebody else worked on. Okay. Ooh, I just saw one I really liked. Ah, this should be good. I hope that okay, the document is gone. There was one I saw before this screen. Give me just a moment. This one here. I like that. Okay. Let me see. Let me try to make this big and just try to look at this where it is. It seems to be a struggle just to find a good periodic table. Okay, let's see. I may have to open this. I hope this is not fraudulent. Okay, we'll find out in a little bit. No, because I didn't realize I had to download stuff. I'm like, come on, can I just get a page? What happened to the days when the internet was just free? Oh, there it is. Oh, that's nice. Okay, I take it back. I take it back. It was worth it. Okay, so where is sodium? Sodium is right here. Once sodium loses that one electron, how many electrons does it have left? So real quick here, it goes from sodium, sodium, work with me here, with 11 electrons, and then it becomes sodium ion, okay, with 10 electrons. So something is happening to where this is very slow. Okay, sodium ion with 10 electrons, okay? So what element has 10 electrons? Let's find it right here, neon. Remember, this is our group 8 element. Sodium can become like neon, which is stable, by losing one electron, okay? So while we're here, I want to mention this. Elements achieve stability if they're going to lose electron by either losing one, two, or three electrons. As long as losing one, two, or three gets them to have the same number of electrons as any of these group 8 elements, okay? You see where chlorine is. Chlorine is too far from neon. If chlorine was planning to be like neon, chlorine would have to lose 7 electrons. Elements can only lose 1, 2, or 3. Not beyond 3. The level that we're learning right now, 1, 2, or 3, and that's it. They can also gain 1, 2, or 3. And elements can gain electrons for stability. So chlorine's only option here is to gain one electron to become like argon. So when sodium gives up its one electron, chlorine takes it, and chlorine goes from chlorine, oh, come on, computer, 17. I may have to restart this later to make it faster, to becoming chlorine 18 with a negative charge. Bear with me, y'all. This is the internet. This is the whole internet. Okay. So in both cases, now it has the behavior of neon. Chlorine ion has the behavior of argon, meaning they're stable. Well, if they're stable, why do they form a bond? They form a bond because even though they became stable, look at what they did. They formed charges, and these charges are opposites. So opposites attract. So the reason why they bond is not because they exchange electrons, it's because they formed opposite charges and they can't resist each other. They're now drawn to each other by the opposite charge. So sometimes you will see documents out there referring to the ionic bond as an electrostatic force of attraction. All they're saying is the oppositely charged elements got together and they formed a bond. Okay, so Na attracts Cl and they form the compound. Okay, and so that's true. When it comes to covalent bonds, though, which we spend most of our time with covalent bonds, when it comes to covalent bonds, this is a whole different story. Okay, with covalent bonds, you're having a bond resulting from the sharing of electrons between two atoms. So over here we have non-metal and non-metal, and they're trying to get together to form a bond. Remember, non-metal elements tend to be smaller. So while I have this periodic table here, I can mention that the zigzag line we see here separates the left elements, which are mostly metals. These are metals right here. Everything in here, metals, all of these. And then on the right, most of these are non-metals. Okay, you see how they drew hydrogen in both groups, metal and non-metal. Hydrogen has behavior of both groups. Okay, so there have been arguments in the past where they said that hydrogen belonged to this group right here because of its behavior, right? And then there are arguments in the past where other groups are like, no, we are passionate. Hydrogen belongs to this group right here. So the author of this periodic table is a reasonable person. He's like, why don't we make both groups happy and put hydrogen in both places so everybody's happy? Okay, so recognize that. Hydrogen has a behavior of both. Okay. The elements close to this area right here, these are called metalloids. They have the behavior of both groups. So I'm usually wondering, why not put hydrogen right there? Because hydrogen has very unique properties, right? It's a lot more complicated than that. But these elements right here, these tend to be on the border. So they have the culture of both groups. They have the behaviors of both groups. Okay. Okay. Once again, metals, non-metals. So with the non-metal group, this the tiny group on the right of the zigzag, these tend to be small in size. So small in size. When you're judging a covalent compound, once again, look at the first element. Is the first element a non-metal? Check. Second element, non-metal? Check. You were dealing with a covalent compound. Okay. And so how do these form bonds? They form bonds by sharing electrons. So let me go over here and then we'll make sure I want to make sure we're making progress in the slides. We talked about ionic bonds. Remember, these are metals on the left side of the periodic table. I just showed you guys that. Non-metals on the right side of the periodic table. We saw how they form compounds. This is showing you the elements in their standard state. And this is showing you what happens when a compound is made. This is actually not balanced. I'm going to balance it right now. It's bothering me. Like, how can they not balance the equation? Anyway, sodium metal looks very shiny. Chlorine gas is like a greenish gas, but then sodium chloride is tasty salt crystals, right? This is just salt. Okay, so I talked to you about ionic compounds. We're going to spend most of our time discussing covalent compound and covalent bonding because most of organic chemistry is a story about carbon and the bonds it makes. Carbon and bonds it makes. Not just the bonds it makes, but the formulas it makes. So carbon tends to bond with covalent bonds, okay? So real quick, before we get into covalent bond, I mentioned this to you earlier about the bonding ability of elements. So I want to talk about it before I move on real quick. When it comes to ionic bonding, so let me minimize this right here. In ionic bonds, I mentioned this, that elements that are about to lose electrons, elements that lose electrons can lose up to 3 electrons. Okay, they can lose 1, 2, or 3 electrons. When it comes to the so these will be your metals, of course. When it comes to your non-metals, these lose, non-metals are doing the opposite. These gain up to 3 electrons. So they can gain 1 or 2 or 3. And so down the road, we'll come back and revisit this concept. But for right now, we're looking at the different types of bonding in general. If an element can neither gain 3 nor lose 3, then the only thing that element can do is share electrons. So now we're bringing in covalent bonds. So covalent bonds are formed when two nonmetals combine or when a metalloid, remember the metalloid are the elements on the border? A metalloid forms a bond with a nonmetal, okay? So when we talk about the compound formed, covalent bonds are formed in molecular compounds. So we're told here that a molecule is essentially a group of atoms where the atoms are sharing electrons. So this has to also do with your size. So here, notice they said 2 non-metals. And what's our first example? The ambiguous element hydrogen. Okay, so real quick here, we're seeing 2 hydrogens coming together and they're forming a hydrogen bond. They're forming a bond between the hydrogens, right? And this bond is actually called a covalent bond. We'll learn about hydrogen bonds down the road, not in this chapter, the next chapter. Okay, this is called a covalent bond. How do we know it's covalent? It's how they got together. So covalent bonds are formed by sharing electrons. So which electrons are shared? For the most part, the electrons that are shared are the unpaired electrons. So I'll say here as a rule, and when I write these rules and stuff, please make sure you're taking notes. Unpaired electrons are shared. Okay? So the other way of stating this is the number of unpaired electrons equal the number of covalent bonds. You see where I'm going with this? So we can look at an element's position in the periodic table. We can figure out what these dots are. These, by the way, are called Lewis dots. These are going to be unfolded with time. I'm going to start unfolding things earlier because I feel like we're referring to them before we define them. Okay? The number of unpaired electrons equal the number of covalent bonds. So when we're looking at this structure here, these are actually called Lewis symbol for elements. So I want to go ahead and cover that right now. The Lewis symbol for elements, because I think it's part of your lab. I did a lot of work, y'all, the past few days to prepare for this class. So yeah, I think you have to work on a Lewis symbol for elements. To get the symbol, electrons are drawn as dots. The number of dots equal the group number. Okay, so this is how you get the Lewis symbol for the element. You have to know what the element is. You have to know its group number, and then the number of dots equal number of group number. Okay, and then once we decode that, then we can see how we're actually making this bond. So real quick, let me pull out my periodic table. We're going to be writing on this periodic table a lot. Okay, let me see if I can release or erase this, at least some of it. I'm mostly dealing with group A elements. We're not going to be dealing with the group B because they're complex. So what I'm going to do here is on top of this group. So remember, groups are judged vertically, right? So let me see if I can draw a straight barrier here. We're only dealing with the A group. I really like this periodic table, by the way. So 1A, this will just have an element with one dot. So I just put X for the element. I have no idea what the element is. And then 2A will have an element with two dots. I have seen books do it differently. Some write the dots on opposite ends, some clump them together. It's up to you. It doesn't really matter. I think it's important to leave them separate though, because remember, number of unpaired electrons equal number of covalent bonds, right? So don't pair them. Okay, 3A. The element is surrounded by three dots. 4A, the element is surrounded by four dots, and it goes on and on and on. I can't write anymore. 5A, the element is surrounded by five dots. 2, 3, 4, 5. Okay, and it goes all the way to the 8 dots in this group right here. 1, 2, 3, 4, 5, 6, 7, 8. Right. Let me finish this too. I've come this far. I can make it. I can make it. 1, 2, 3, 4, 5, 6. Oh my goodness, 7, 8. You get the 8. Oh, what am I doing? That's supposed to be 7, not 8. Oh, it's supposed to be 6. I went out of order. Oh my goodness. I should have kept with the order versus skipping over and then coming back. You get the idea though, right? We got I just undid a bunch of things. We got 3 here, we got 4 here, we got 5 here, we got 6 here, we got 7 here, we got 8 here. It's a lot easier for me to write on the iPad than to write with my mouse with a slow computer. Okay, so understanding this, we see that hydrogen is in group 1, right? So back here, it's in group 1, so it has one dot, one unpaired dot. So if hydrogen is going to form a bond, how many bonds will it form? It will always form one bond. So now we're back to what we're looking at. Hydrogen has one unpaired electron. It's about to form a bond with another hydrogen, one unpaired electron. Based on the number of unpaired electrons, this one here can form one bond. This one here can form one bond. Okay, the other information we need to know is that 2 electrons are needed per bond. So 2 electrons make up one bond. Okay? So if these can only bond with one bond and these can only bond with one bond, when you bring them together and they share their electrons, guess what? These are now shared electrons. They become essentially a bond between the hydrogen, and this is now called covalent bond. Okay, we'll be doing this more and more. We have a lot more assignments where we work on this to give you guys practice before we get to chapter 10, which we're getting to, is it on Monday or Tuesday or something like that? Yeah. Okay. So now that we've seen covalent bond, we're now going into, I have mentioned this before, so now this is a review. I'll go over this real quick. By losing 1, 2, or 3 electrons, going back to the ions, right? An atom forms a cation with a completely filled outer shell. Okay, so we're told here when these electrons, when the metal loses 1, 2, or 3 electron, what is now revealed is a completely filled outer shell of electrons. So for those of you who want to understand everything, I'm going to answer that question for you, which is, well, if you're losing electron, how is a completely filled outer shell revealed? For me to illustrate this part here, I'm going to go back to the example I gave you guys with sodium. The good thing about you guys watching this video at home is that you're free to rewind, stop, and watch this over again, right? Let's start with sodium losing electrons. I'll have sodium here losing 1 electron to become like neon. So let me show you how this works out, okay? Sodium, once again, has 11 electrons and is about to lose 1 electron. I'm going to use the energy level diagram to show the electrons distributed or sorted around sodium. So they're usually sorted in this order. 2 electrons on the first energy level, 8 on the second, and based on the number of electrons that sodium has, 1 will be on the third energy level. They tend to use this in biology, and I'm kind of stealing from biology because this is the simplest way I know how to explain this, okay? So I'm going to draw 3 rings, and these rings will represent the energy levels. So it's kind of like what we discussed with Bohr's model, okay? With sodium being right here in the middle, and that's the nucleus for sodium. So energy level 1 has 2 electrons. Energy level 2 has 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Energy level 3 has that 1 electron. When we say sodium loses 1 electron, this is the electron that's lost. So electron that is lost. Okay. So if the electron is lost, the electron is gone, and so is its energy level. It leaves with that whole ring. So what do we have now? Now we have sodium ion, right? The inner ring still exists with its 2 electrons. The outer ring still exists with its 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8, right? This is now what sodium ion with 10 electrons looks like. It's a lot smaller because the whole outer layer got lost. The energy level got lost, and so did the electron. Well, do you see how the new outer layer has 8 electrons? Okay, so I was learning this when I was really, really young, many years ago. Like it feels like a million years ago. And I'm looking at this and I'm thinking, how can I relate this to my life? I'm like, this is kind of like exfoliating, right? If you exfoliate, you understand. You're trying to get rid of dead skin. This is not dead skin. We're trying to get rid of the outer layer to reveal fresh new skin that's lacking blemish or something, whatever, microdermabrasion, stuff they do to remove outer layers, or sanding, right, for cars. If you're sanding the outer layer that maybe is rusted or something to reveal a new, fresh looking lower layer, that's what we're doing here, only with the electron though. The electron gets lost, the outer layer gets lost, what gets revealed is a new layer that has 8 electrons. Okay? So that's how This will happen when one electron is lost, 2 or 3. The outer layer that comes out is actually full. And by gaining 1, 2, or 3 electrons, the other atom, remember the non-metal, can also end up with a completely filled outer shell of electrons. Once again, since I explained this for sodium, let me tell the story from the point of view of chlorine. So chlorine has how many electrons? What happened to my periodic table? I'm trying to illustrate these to you so that the concepts make sense. Okay. So chlorine is right here. Chlorine is gonna gain 1 to go from 17 to 18. Okay. So chlorine has 17. And so for 17, let me see. 2 will be on the first energy level. The second energy level goes all the way up to 8. The third one also goes all the way to 8, but currently we have 2 plus 8, which makes 10, right? And then 7. So I'm going to draw 3 energy levels for chlorine. Chlorine in the middle. This is the nucleus. First energy level. Second energy level. I'm just going to put my electrons there. Third energy level. So I need 3 different layers. The first 2 go here. The second set of 8. 1, 2, 3, 4, 5, 6, 7, 8. 8 go there. The last layer has 7. 1, 2, 3, 4, 5, 6, 7. Okay? You see how it's so much easier to see that the quickest way for chlorine to get to 8, oops, I didn't realize it was covered. The quicker way for chlorine to get to 8 is just to add 1 electron right here. So chlorine gains electron, right, from sodium. And when it does so, can I cheat and just copy this picture? Let me see if I can copy this picture because I may be able to just do this. Oops. Copy. Let me see if it allows me to paste. Paste. Yes, right here. Okay, so let me go ahead and say we add the last electron. So this will be the new electron. Let's give it a different color, blue. This is the new electron that came in after the fact. Okay, so after the new electron came in, chlorine now has 18 electron in the order 288, right? This is a new electron, as you can see. Now we have 8 electrons in the outer layer. Okay, so having 8 electrons is the goal, and 8 electrons is considered stable. Okay, and since 8 electrons tend to be the goal for many elements, the goal is to get to 8 electrons, to be surrounded by 8 electrons. They call this the octet rule, or known as the rule of 8, right? So if you've heard the terms octet rule, then that's just the rule that says elements have a goal. And what's their goal? Is to be surrounded by 8 electrons. Why? Because for them, 8 electrons symbolizes stability. Okay? So there it is. And we're told here, octet rule, a main group element is especially stable when it possesses an octet of electrons in its outer shell. So we have seen how both metals get 8 layers by exfoliating the outer layer, right? As they lose 1, 2, or 3 electrons. Nonmetals don't exfoliate. They can't shed 7 electrons. The rule was you can only go up to 3, right? You can lose 1, 2, or 3. So they just gain 1 electron to then have 8 electrons in the outer layer. It's interesting the lengths that elements go to meet their goals, right? So now I can read through this part real quick, right? Because I've kind of gone over it. So we're told we're relating group numbers to the ionic charge for main group elements. Oh, sorry, it's an email. This is, sorry, y'all. This is what life is like for faculty in the end of the semester. It's just email blast, 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 right? I'll deal with them later when I'm trying to relax. Okay, so elements in the same group form ions that are of similar charges. So we see right here, when we're dealing with metals, metals form cations. Cations is another word for positive charge. So cation is called cation, not cation. So I was telling my husband one time, and then the cation, he's like, cation? What do you mean cation? I said, it's cation, like Cation. He said, what do you mean cation? If you say this is cation, then what do you say this is? I said, the vacation. He said, no, but cation. I said, this is not chemistry. Oh my goodness. This is how we pronounce this word. Okay, I don't know the etymology or the origin of the word. All I know is it's pronounced cation, and then vacation is still vacation, not vacation. Okay, so don't ask me all those words, right? Metals form positive charges. So when a metal loses one electron, it forms a plus one. Okay. So we're told for metals in group 1A, 2A, and 3A, the group number is equal to the charge of the cation. So going back to this, I'm just going to write it right here. So all these elements in group 1, these right here, all the way hydrogen to francium, they tend to form a charge of plus 1. Okay, the ones in group 2, because the outermost electrons are 2, they can be lost. They form a charge of plus 2 or 2 plus, either one. The ones in group 3, because they have 3 electrons, tend to form a charge of plus 3 or 3 plus. Remember, group 4 is surrounded by 4 electrons. It can't lose all 4 electrons, so it cannot form plus 4. Okay, so here's where I'm going to actually take the time. And then we can see, let me take the time and fix this because I'm trying to relate it to the group. Okay, let me write this, take my time and write this better. Okay, so for group 5, we have 1, 2, 3, 4, 5. You can see group 5 cannot lose all 5 electrons. So what it ends up doing is it ends up gaining 3 electrons to get to 8, right? So we put 3 minus because it gains 3 electrons. And then for group 6 starts off surrounded by 6 dots. So 1, 2, 3, 4, 5, 6. Group 6 surrounded by 6 dots, it can't lose 6 dots to reveal the layer of 8. So it gains 2 dots to get to 8. So once again, I'm going to draw the 2 dots in a different color. Let me get a more bold color right here. A dot right here, and it gains a dot right here. Okay, 2 dots to get to 8. So we'll put 2 minus because it gained 2 dots. And then finally, we have group 7, like we saw with chlorine, right, or fluorine, or anything in that family. Group 7 starts off with 7 dots. I'm going to draw 2 big ones on the bottom here. 2, 3, 4, 5, 6, 7. Group 7 will gain 1 electron. I can put this here to get to 8. So this gains a charge of minus 1. Okay, so it's kind of like a palindrome. Plus 1, plus 2, plus 3. Skip group 4. Minus 3, minus 2, minus 1. Okay. Nonmetals form anions. And we're told here for nonmetals, the charge of the nonmetals is 8 minus the group number. So the other way you could have gotten that, think about it. For group 5, 8 minus 5 is actually the opposite. I'm seeing 8 minus a group number. It's actually the opposite. Because nonmetals have a negative charge. So I'll actually say for group 5, the group number minus 8. Right, so it's 5 minus 8 to give us a charge of minus 3. And then for group 6, same thing, group number minus 8. So we got 6 minus 8 to give us minus 2. And then group 7, same thing, 7 minus 8 to give us minus 1. So you just remember it as plus 1, plus 2, plus 3, skip 4, minus 3, minus 2, minus 1, and that works out that way. So I'll look at this in a second here. Yeah, so they show it to you right here. Group 1A, these are all plus 1. Group 2A, these are all plus 2. This is their common bonding pattern. Group 3A, they're plus 3. Skip over group 4, and then you have minus 3, minus 2, minus 1. So you have plus 3 here, you have plus 1, and we have plus 2. Okay? Of course, remember you have access to these PowerPoint slides. And the goal is to have the outer layer of energy in the atom have 8 electrons. Since group 8 starts off with 8 electrons, it doesn't need to gain or lose electrons, right? It's already stable. Okay, so here they're just showing you more information. Once again, I did this already. Since group 1 metals tend to have 1 electron, they can only lose 1 electron. Group 2 metals have 2 electrons, they lose 2 electrons. Group 3 have 3 electrons, they lose all 3 electrons. Okay, so this is showing you how the electrons are lost. With the non-metals, group 5, 6, 7, as it shows right here, they have how many? 5 electrons. So you just add electrons to the part that's unpaired. Add an electron here, here, and here. You added 3, so they end up with a charge of -3. -3 is the number of electrons that got added, right? So you add electrons where you have unpaired electrons, and that gives you -2. Here you have 1 unpaired electron, so you need 1 more to get to 8, and you have -1. Okay? So just kind of a restatement of what I already said. Now, I already told you guys before, finally, you have these oppositely charged elements attracting each other to form the ionic bond right there. Okay, so you want to be aware that when you're forming an ionic compound, essentially the goal here is to have a 0 charge overall, right? So you pick the number of ions necessary to give an overall charge of 0. So they're showing you here, it's illustrated, that in sodium chloride, so sodium forms a charge of +1 when it forms an ion, and chlorine a charge of -1. Then you want 1 of each ion to make a compound, right? Because you want to make sure the ions cancel out. And over here, since lithium is +1, each lithium is in group 1, so it loses 1 electron and forms a charge of +1. But if you want to combine this with oxygen, oxygen has a charge of -2. You're going to need 2 lithiums. Each lithium will be +1, so that together they have a charge of +2, so it can balance out the 1 oxygen's charge that's -2. So in the compound, you see right here, it says it takes 2 lithiums to be able to handle and neutralize the charge on oxygen. Okay. On this side here, you have barium combining with iodine. Each iodine has a charge of -1, and barium has a charge of +2. So it takes 2 iodines to neutralize barium, right? Each of the iodines is -1. So we can add up to -2 here. Barium is +2. Okay, now with this one here is a little bit more complicated. In this formula, it shows it takes 2 aluminum. Let's see. Each aluminum is +3, right? So each aluminum is +3. It takes 2 aluminum to get to +6. Each oxygen is -2. So how many oxygens does it take to get to -6? Do it 3 times. -2 plus -2 plus -2 gives you -6. So in order to get the neutral compound, you're going to need 2 of the aluminums and 3. I'm literally drawing over 3 and saying 1. 3 of the oxygens. You know what? My mind was trailing off to something else. I forget if I gave you guys the assignment where you're comparing number of protons and electrons in the ion. I forgot. I may have deleted that. Okay, because now I want us to end with we're not ending the chapter, just ionic compounds and going into molecular compounds. Ionic compounds, when I think about this, think table salt. I like to anchor new information to something I know. Oh, look, and they had that here. Ionic compounds are crystalline solids, right? If you take a grain of salt, it looks like a crystalline solid. They have a very high melting point. Have you ever tried to melt salt? Your answer should be no. But if you have, it's very difficult to melt salt. You have to get it this hot for it to melt. It has a very high melting point, an extremely high boiling point there. Ionic compounds are not easy to melt. Covalent compounds are very easy to melt, such as sugar. You can melt sugar and make, what's the thing called? Caramel. Ooh, caramel. Anyway, yeah, sorry. I need to focus. Yes, you can melt sugar and make caramel. You cannot melt salt and make the caramel version of salt. Okay. Anyway, so ionic compounds dissolve in water. So when ionic compounds dissolve in water, they actually separate the cations and the anions that used to be together. Remember, the sodium ion is the cation. It got together with the chlorine ion because of that strong electrostatic charge. Opposites attract. But if you want to separate them, don't separate them by melting. They're still together when they're melted. They're still together when they're being boiled. If you want to separate these ions, even though it seems like it's impossible to separate them, just put them in water and they will separate. Okay? So when they separate, they actually conduct electricity. If you work out or if you just like taking Gatorade, Gatorade is considered Gatorade, an electrolyte because it has ionic compounds whose ions are separated. And so Gatorade can actually conduct electricity. Okay. So compounds where the positive ion got separated from the negative ion can conduct electricity. Okay. So, guys, I'm struggling because I'm trying to get deep and I'm like, no, this is a non-majors class. Keep it simple. Keep it simple. Okay. So right here, as we wrap up talking about ionic compounds and we're moving to molecular compounds here, we're talking about some useful ionic compounds. During this week, stressful week of final, ionic compounds are very helpful, right? We see them here in over-the-counter drugs such as calcium chloride, or sorry, calcium carbonate, and this is in Tums, right? The antacid Tums that helps to settle your stomach. Magnesium hydroxide, this is in Maalox. I think that's how you pronounce it, right? Maalox. And then you have iron 3 sulfate, which is the iron 3 sulfate. This is iron pills. If you've ever had this, it tastes nasty, right? It tastes like metal. This is a supplement that's used to treat anemia. So if you, for whatever reason, you have low anemia, you may be put on this supplement. Nasty stuff. But anyway, yeah. So remember, this class is for people who are interested in health fields. So we will talk about health references more than you have seen in your other chemistry classes. Give me just a moment. Hold on. I'll be back. And I am back. Okay, so as we gear up for the covalent bond, I want to talk about the sharing of electrons. I've already discussed this, right? How the hydrogen atoms get together to form the compound, so I won't do that anymore. What I want to talk about here is how can you judge based on the Lewis structure of the element, not the compound, just the element, what type of bonds it will form and how many bonds it will form. So I did go through before, right, and talk about group 1 elements such as hydrogen. Let me add a page here. So real quick, let me pick some random elements in the periodic table. Instead of talking about hydrogen here, I can talk about sodium. Sodium will normally form one bond. How do I know that it has one unpaired electron, right? I can then just throw in there beryllium in group 2 right here. It has two unpaired electrons. Most likely, you can hypothesize it will form one bond. Let's go to 3A, boron. Okay, boron, what do you think it will form? Yeah, based on the sequence, it will form three bonds, right? Now, the bonds can be grouped together, but essentially, based on the number of unpaired electrons, it looks like that. Like this. And then, well, I don't have room, but yeah, you get the idea, right? One bond from sodium, two bonds from beryllium, like that. Okay, so now that I have exhausted all that, let me now move to uh, the SNOF group. So I'm going to call this group out early on. SNOF is this group right here. We're done with beryllium, right? Let's see. I call them SNOF. Carbon, nitrogen, oxygen, fluorine. Snuff. You can call it knuff. You can call it whatever you want to call it. I call it snuff because we tend to focus on these elements a lot in organic chemistry. And you see that when we get to chapter 10. Carbon, nitrogen, oxygen, fluorine. So you want to make sure you are aware of their bonding patterns, what is normal, what is not normal. Of course, and hydrogen. We see hydrogen a lot. So I want to examine right now hydrogen, carbon, nitrogen, oxygen, and fluorine for us to see what's going on. So with hydrogen, of course, we know it's in group 1, so it will normally form one bond. Carbon is in group 4. So it starts off with 4 unpaired electron. Nitrogen is in, I should draw this a little lower, group 5. So we start off with 3 unpaired electrons. Then we have oxygen in group 6. So we start off with 2 unpaired electrons. Then we finally end up with fluorine in group 7. We start off with 1 unpaired electrons. So remember, number of unpaired electrons equal bond. Okay? And that's for covalent bond, and in some cases ionic bond too. Okay, so we expect that the normal bonding pattern for hydrogen will be just one bond. Okay, so looking at this, hydrogen has one bond, no lone pair. So one bond, 0 lone pair, right? Carbon will normally form 4 bonds, 0 lone pairs. So LP here stands for lone pair, just in case you're wondering. Right here, lone pairs. Okay, what about nitrogen? Nitrogen has 3 bonds, and then you see that? 3 bonds, 1 lone pair. What about oxygen? 2 bonds, 2 lone pair. You want to make sure you remember this bonding pattern. 1 bond, 3 lone pairs. Okay? Because we're going to start seeing this as a whole, and then it gets interesting. That's the word I'm going to say. Very quick. As these form a bond here, the unpaired electrons are the ones that pair up. So that's how they form the bond right here. So now fluorine has 3 unpaired electrons and hydrogen has 1, right? And so what we're seeing here is because they're sharing the electrons, they're essentially forming a covalent bond. Hydrogen ends up with 2 electrons, and then fluorine ends up with 8 electrons. So I'm going to say this right here as we talk about the rule of 8 or the octet rule. I need to add this. With the octet rule, of course, says this, that atoms share, lose, or gain electrons to be surrounded by, let me change that, to be surrounded by 8 electrons. That makes more sense. Electrons. Oh, I can't spell. 8 electrons. Okay. So we have exceptions to this rule. For the exceptions, elements before carbon are not able to have 8 electrons. They just don't start off with enough electrons. Okay? They don't start off with enough electrons. For that reason, they just don't do so great with 8 electrons. So let me see. With this part right here, let me use this right here. Oh, come on, people. Okay. So anything before carbon, that means boron, beryllium, lithium, helium, hydrogen. Oh, sorry, hydrogen. I'm like, why do we have hydrogen twice? Okay, so exception. Hydrogen. Let me pull this up here so y'all can see. Hydrogen, helium, lithium, beryllium, boron. These are elements that appear before carbon and they're not able to get to octet. So when you see them, resist the desire to double bond them because they will never get to octet and they're content that way. Hydrogen will only form 1 bond. Helium will be surrounded by 2 electrons. Lithium will form 1 bond. Beryllium will form 2. Boron will form 3 leave it as is. Okay. Finally, we're kind of moving on to the kind of the general chemistry part, looking at Lewis structures. With Lewis structures, we're going to be talking about the rules about drawing Lewis structures. So before we get into that, I want to mention this. Lewis structures, this, to draw the Lewis structure, which is this right here, I'll call it Lewis structure, LS, you have to be given the formula first. So CH4. And then from there, you draw the Lewis structure. We'll go through the steps of doing that. And then right here, we have what is called a Vesper, actually written Vesper, but it's difficult to say Vesper when you're talking, so they say Vesper. Valence shell electron pair repulsion theory, or the model. So with Lewis structure, the bond are usually drawn in a vertical and horizontal fashion, right? A little bit of a kind of OCD there. Everything is so neat and packed and organized. But with the valence shell electron pair repulsion, we see the bonds having an angle. Okay? I just wrote angel, didn't I? It's supposed to be angle, yo. Excuse my spelling. Oh, for those of y'all who don't know me, my spelling, my grammar, my adding, it's a trip. Okay, so this is Lewis structure, and right here we have Vesper model where the bonds are not drawn 90 degrees to each other. Okay, same thing here. This is Lewis structure, and here we have Vesper model or Vesper. So now that we've done all this, this is a repetition. I don't know why we have this again. Oh, I talked about the bonding pattern, right? I'm kind of getting ahead of myself, but it allows me to skip this part. So please notice the number of bonds. This is normal, okay? It's important for us to see this right now. As I said, this is a warm-up. So if it seems easy, do not judge the rest of the class by this first chapter, because this is just a warm-up. There's a reason why I brought this back in, okay? If you look, with the exception of hydrogen, the number of electrons surrounding each of these common elements, right, the SNOF group, is 8. You have 8 electrons via 4 bonds, 8 electrons via 3 bonds and 1 lone pair, 8 electrons here via 2 bonds and 2 lone pairs, 8 electrons via 1 bond and 3 lone pairs, okay? So I want to move on and talk about how we draw Lewis structures finally. When we're looking at Lewis structures, it's important for us to know the structure of a formula, okay? So a molecular formula shows the number and the identity of all the atoms in a compound, but not which atoms are bonded to each other. So with the Lewis structure, we are able to see the connectivity between atoms as well as the location of all the bonding and non-bonding valence electrons. So here's the bottom line. Within the atom, the outermost electrons are the ones that get exchanged to form bonds. These outermost electrons are called the valence electrons, the outermost electrons. They're very close to the edge of the atom, okay? So we're going to go over rules for drawing Lewis structures. This is, yeah, it's end of semester. Number 1, it says draw only valence electrons. Number 2, give every main group element except hydrogen and an oxide of electrons. Give hydrogen only 2 electrons. Okay, we'll do that. Okay, so here it says how to draw a Lewis structure. Arrange the atoms next to each other so that you think are bonded together. What? Okay, listen, I haven't modified the slides. I'm just reading what they're saying and I'm following along. Let me tell you how this works. When you're given the formula, so the formula they gave us here is CH3Cl, okay? The element that has the greatest bonding ability is the one that goes in the middle. Remember how I showed you guys the bonds here? I said 1 bond, 2 bonds, 3 bonds, 4 bonds, 3 bonds, 2 bonds, 1 bond. The one that has the greatest bonding ability is the 4 bond, which is this right here, group 4. Okay, greatest bonding ability. So if your formula they gave you has a carbon in it, guess what? Carbon automatically goes to the middle. Why? It has the greatest, it can form the greatest number of bonds, 4 bonds. Okay, so the official rule though is that I'm going to paraphrase it right here. The least electronegative element is central. Okay? I'll just say the one that can form the most bond. Hydrogen is never central. Never. So I'm going to erase this part. Remember, you guys can pause and rewind, right? Hydrogen is never a central atom. For you guys' level, never. In grad school, something happened one day. I just packed up my bags and left for the day because I was like, I've had it. They violated the rules, the octet rule. But you guys know dealing with that. So carbon is in the middle. You place carbon in the middle, surrounded by the remaining 4 elements, right? So we have 3 hydrogens here and 1 chlorine. And then they're telling you use the common bonding patterns from figure 3.5 to arrange the atoms. So what I like to do here is, before I do anything, you have your carbon in the middle surrounded by chlorine and then the 3 hydrogens. You want to figure out what your total valence electrons are. So count the valence electrons. The valence electrons equal group number. Okay, once again, everything is kind of around the periodic table. You see where carbon is? It's in group 4. So carbon brings in 4 electrons. And then what did we have? We had chlorine in group 7. Chlorine brings in 7 electrons. And then we also had, what was it, hydrogen? Yeah, hydrogen in group 1. So each hydrogen brings in 1 electron. So let me scroll down here and you can see. In the formula, we have 1 carbon. The carbon brings in 4 electrons. We have 3 hydrogen. Each hydrogen brings in 1 electron. So these are the valence electrons. Remember, valence electrons equal group number. Okay, so when you add all these, we figure out that this formula here contains a total of 14 valence electrons in its structure. So now we have to know how to distribute this. So we start off, okay, they kind of skip straight to the end. Let me kind of detour and finish this myself, and then I'll just see what they're doing. We have 14 electrons to work with, right? We have carbon in the middle surrounded by 3 hydrogens. And then we have chlorine right here. We have 14 electrons to work with. You want to place single bonds between the central atom and the outer atom first. So single bonds, single bond, single bond, single bond. I just made 8 single bonds. Remember, one bond is made up of 2 electrons. So of the 4 bonds I made, I essentially used up 8 electrons. So from the 14, I used up 8 electrons and I'm left with 6. Okay, the next step is to make sure the outer atom that is not hydrogen has an octet of electrons. You do so by adding 6 electrons as 3 pairs of electrons to the outer element that's not hydrogen. So by placing these 3 electrons here, now this chlorine has an octet of electrons. How? 6 electrons as lone pairs. And then 2 electrons as 1 bond, right? 2 electrons as 1 bond. What about carbon? Has 2 electrons here, 2 electrons here, 2 electrons here, 2 electrons here. Carbon now has 8 electrons. Okay. So I just used the 6 electrons to make this -6. I'm at 0. When you're working with the total valence electrons, you have to make sure you empty it out. Empty out your total valence electrons on your Lewis structure. Now let's check. Chlorine has octet, good. Carbon has octet, good. Hydrogen has duet. Remember, hydrogen uses duet rule. So duet, octet, and octet. So this is the Lewis structure right here. Once again, feel free to pause and go back and move forth. I mean, go back and forth, whatever you need to do to go over that again. Yep. So they go through that, they explain that to you, and in the end, we end up with essentially using all the electrons available. Now we're moving on to a scenario where you have to form multiple bonds. What do you do when you have to draw multiple bonds in this scenario here? So what I'm going to do is I'm going to draw this structure here, and then I am going to come back and see what they did. I'm adding a page. I'm detouring because they're following a very different process. So we're going to be drawing CO2. Like before, we itemize. We have carbon, we have oxygen. We have one carbon. Each carbon is in, I wouldn't say cheat. Let me use the periodic table as a resource to help you all learn, right? And to to remind me too, because I can feel the fatigue kind of setting in. It's been a long day with meetings and stuff. So carbon is in group 4 right here, right? So from carbon, I have 4, 1 times 4. And then from oxygen, it's group 6. I got 6. But in my formula, I have 2 oxygens. So 2 times 6 equal what? 12. This is 4. 4 plus, oh, my bad. Let me scoot this over. I don't need this anymore right now. Right now. Okay, 4 plus 12 equals 16. Okay, so now we have CO2. With CO2, let's see, CO2, we end up with 16 valence electrons. Now my central atom is going to be carbon, because I told you guys whenever carbon shows up, it's most likely the central atom. So carbon is going to be what? 1 carbon here surrounded by 2 oxygens. Okay. Okay. We have 16 electrons to distribute. We'll place single bond here. Place single bonds first. Oops. I have to keep looking up at the screen and realizing I'm blocking that. 2 bonds makes use of 4 electrons, and we're left with 12, right? And then you want to place 6 electrons on each surrounding element that's not hydrogen. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So minus 12. 6 times 2 is 12, right? Minus 12, we're down to 0. Okay, let's see. Now, these oxygens have 80 electrons each. They've reached octet status, right? So they're happy, they're stable. But what about carbon? Carbon only has 4 electrons. So how do we help carbon get to 8 when we don't have any more electrons from here? So what we do is we take 2 electrons from each oxygen, and we have the oxygens share. We don't want to compromise the status that oxygen has, but we want oxygen to help carbon out. So we do so by sharing. Sharing is just shared custody. When we're making a bond, then the elements holding a bond both have equal access to the electrons in the bond. Okay, so it goes from belonging to oxygen alone in a lone pair to belonging to both oxygen and carbon. Now we can say carbon has 8 electrons. Every one or every element in the structure here has 8 electrons, and essentially all of these have octet. They have achieved the status of octet. Okay? Yeah, so we're practicing drawing that. Remember how I told you guys about the valence shell electron pair repulsion theory? We use that to figure out the actual shape of the molecules. While Lewis shows us a very neat model where everything is all vertical and horizontal and is very organized, in reality, molecules exist in the form of the VSEPR model. So molecules have the VSEPR model shape more than they do the Lewis's shape. Okay, so if we're trying to figure out the shape of the molecule, you have to go through VSEPR theory. To determine the shape around the given atom, first determine how many groups surround the atom. Okay, if you've had 1405 before, you've had this before. This is a review. We tend to determine the shape around a given atom. We do it atom at a time. So a group is either an atom or a lone pair of electrons. That's a neat way of looking at it. Okay. I'm going to stick with their way since that's what they said. A group is either an atom or a lone pair. So an atom can be any symbol or a lone pair like that of electrons. Okay? Then use Vesper theory to determine the shape. The most stable arrangement that keeps the groups as far away from each other. Vesper explains here that there's a valence shell electron pair repulsion theory. All this is saying is, remember the valence shell electrons? These are the outermost electrons. Once these electrons are used in the bond or as lone pair, they are still electrons, so they're negatively charged. They repel each other and stay as far away from each other as possible, forming all those different bond angles. The different bond angles give us the molecular shape. So I know I'm discussing a lot of technical stuff, and you're probably thinking, I need a break. Take a break, come back. Not too long, right? Take a break, come back. Why do we even care about molecular shape? Why is that so important? Because in the world of science, shape determines function, right? The shape of a molecule determines the function of that molecule. Well, okay, science is selfish. Anyway, this is my opinion, right? Science is selfish. We tend to look at things, objects, entities, creatures from the point of view of our own experience, right? We we kind of, what's the term, anthropomorphize. I can't say very well, but we kind of make them like humans, right? Like they have a purpose and they have a desire and now they're happy based on our perception of what they're doing. So from our experience in experiments, the shape of the molecule ties into the function. So if we know the shape, we can almost predict the function or the behavior or even the reaction kind. Okay, so the characteristics of molecules tend to tie back to the shape. So we want to know about the shape. Okay, so when it comes to the shape, let me see how I can skip over these details. For right here, I'm not going to go over the details of all of this. I'm going to skip and go to a table that I have ready for you guys. Okay, to come up with a shape, the first thing you want to do is number one, draw Lewis structure. And guess what? You have this assignment. Draw Lewis structure based on what I just showed you. Once you draw the Lewis structure, you're then going to count the number of elements and it says lone pairs. So let me do one and I'll come back and show you how it works out right here. I just realized I didn't do a Lewis structure that has lone pairs. I'll do ammonia. I'll work on ammonia right here. So with ammonia, NH3, I'm going to draw the Lewis structure for this. Start off with nitrogen. We only have one in the structure. Hydrogen, we have three. Nitrogen is in group 5. You can have your periodic table near you. Hydrogen is in group 1. So we have 5 electrons here. We have 3 electrons here. You add this up and you end up with 8 electrons. Okay. So we now have to place a central atom. Remember, hydrogen is never central. Then the other thing you want to know is if there's only one element and then the other one you have multiples of, the molecule would prefer to have the one element in the center. So in this case here, nitrogen is in the center surrounded by 3 hydrogens like that. Okay, we have 8 electrons to distribute, right? Form single bonds here like that. And the single bonds take care of 6 electrons. We're left with 2. You can't place anything on hydrogen. Hydrogen is now full at a duet. So what we do here with the remaining 2 extra electrons, they go on nitrogen. So minus 2 here, we get to 0. Check it. Hydrogen has a duet, so it's satisfied. Nitrogen now finally has an octet, right? It's surrounded by an octet. 2 electrons here, 2 electrons here, 2 electrons here, and then 2 here. Okay, we were learning about groups, right? How do you count groups around the central atom? Remember, each element counts as a group, and then, of course, you have your lone pair. We did work on, what is it called? CO2 earlier, right? So this one here will have 2 groups. I'm just gonna go through and say 2 groups. We're just practicing 2 groups. or counting groups. And then earlier, what did I work on? I worked on, oh yeah, two groups, because the carbon is surrounded by two atoms, two groups. What else did I work on? This one here, the carbon is surrounded by four atoms, four groups. There's a lone pair on this, but there's no lone pairs directly on carbon, so just four groups. Okay. And then what else do we have here? Then I'm going to detour real quick and show you guys a chart that will help you find this real quick. See right here, for nitrogen, I have 1, 2, 3 groups, and then this here is the fourth group. So this ammonia has 4 groups. Okay, so let me detour real quick because I do have this chart right here, which I will make. Let me write myself a note right here. Add chart. I'm going to make this chart available. Oh, wrong note card. Sorry. I write here notes to myself so I don't forget. I have a little notebook to write notes. Get it? Okay. So I'm going to add molecular geometry chart. Okay, so it seems like I just kind of went from something small to something really big, and this is colorful. Yeah, it is colorful and it's big. Okay. So what I have here is all the possible different combinations you all will need for this class. And it may be a little bit beyond the scope of the class, but it's here for your help to help you. Okay, I'm going to use a highlighter. So what I started off with this is, if you read across, I have sections of rows based on colors. If you're dealing with the element, for example, or a compound, for example, CO2, that only has 2 groups, what is happening here? Okay, let me use the draw feature. It may be a lot easier. 2 groups, right? There's one here, there's one here. So number of electron groups in contact with the central atom, 2. Those 2, this and this. How many of these groups have bonds? See these bonds here? This is a bond, this is a bond. Both of them. Is any of the groups a lone pair? No. So what is the bond angle? The bond angle is the angle between the bonds that you have. We have 2 sets of bonds. You see that? So the bond angle here will be 180 like you would have in geometry if you were dealing with a line. Electron pair geometry or electron pair domain geometry is called linear. This is just the name given to a central atom that has 2 groups. The one you really want to know is the shape. When they talk about what's the shape of this molecule, if you have a central atom surrounded by 2 groups like that, the shape will always be linear. Okay, at some point we'll talk about polarity, so I'll come back to this. But while I'm here and this chart is open, I want to talk about polarity, right? Because essentially that's what we're going to be ending in this chapter right here. This says this molecule is actually nonpolar. When you're judging the polarity of a molecule versus a bond, you want to look at the surrounding groups. This is a central atom right here, okay? Here are the elements that surround it. Oxygen, oxygen. Do the elements that surround it match? Yes. So they're not different. They actually are the same. Does the central atom have any lone pair? No. So the surrounding groups are non-different, and so it's going to be nonpolar. Remember, polar means different. Now it can be different charges, different. Just when they say the situation was polarizing, they're saying the situation was separating people into different groups. Instead of being together harmoniously, it was just creating a separation. So polar means different or kind of separating due to difference, okay? Different. And there's been a lot of polarizing situations lately. I'll leave it at that. Polarizing, right? Trying to use terminology as we learn it. Okay. Once again, here, aluminum has 3 groups. How do I know? 1 group here, 2nd group here, 3rd group. 3 groups. How many of them are bonded groups? All 3. Do we have lone pairs? No. What's the bond angle? Look at the angle between the bonds. Now, I don't like necessarily memorizing. I like I don't memorize the way normal people memorize. I like relating to things I already know. So if you've taken geometry before, you know the bond angle between, if you have a circle is what, 360. If you divide it in half, 360 divided by 2 is 180. That's how we get the linear, like divide the circle in half. If you take the same circle, divide it in three equal parts, imagine this is three equal parts, it's 360 divided by 3, which is 120, okay? Or you can just remember these if that works for you. But you want to be aware of the bond angles. Okay, I'm going to skip this part here and go straight to the shape. When you have three groups like that, this is called trigonal-planar or triangular planar. Yeah, trigonal or triangular. Planar, okay? Once again, non-polar because the three surrounding groups are exactly alike. Now over here, things get interesting. Let me move over to the interesting part. Erase this. You have two atoms, so two groups. Don't forget to count the lone pair. Two dots count as a group. So we have three total groups here. Two of them are bonded groups, and then one is a lone pair. You see that? The bond angle, you have two bonds. This is still 120 because it came from this. But this time the name of the shape is called bent. What? Okay, here's the rationale that I make up because I wasn't there when scientists were deciding this. When scientists look at the shape of this molecule, it looks like a V, like that. And then imagine they were having a meeting and it's like 4 o'clock and they're so tired, like, oh my goodness, what does this look like? It looks like it's like a bent line to me. It looks bent. We'll call it bent. So every time you have something that's not straight and it looks like a V shape, they call that bent. So this right here is called bent. And then now we're saying this is polar. Why is this polar? Look at this. The central, first of all, the two reasons why it's polar. The surrounding elements don't match, right? And then the central atom has a lone pair of electrons. So there are two reasons why this molecule is polar. It's going to be polar, okay? Germanium surrounded by four fluorines. Four groups, right? Four. All four are bonded groups. None are lone pairs. And so what's the bond angle between these four? Even though it looks like 90, don't go by what it looks like. You have to go by this chart, okay? Don't use a Lewis structure to figure out a bond angle. This is a Lewis structure. You want to use the Vesper model where things are actually bent, or just go by the table. Safest way, go by table. The bond angle here will be 109.5. And in the other class where I teach this, I always say when I was struggling to remember this when I was in school, it was like middle school when we begin to learn this stuff. I'm like, I'm not going to remember this. But I was thinking to myself, now I do like back in those days, you had your own favorite frequencies. I know this ages me, really ages me. I had my favorite frequency, it was like 101 point something FM, and oh, they had some great hits. Yeah, yeah. Anyway, so I was thinking to myself, hey, this sounds like a radio station. 109.5 FM. It can't be a radio station because the frequency at this point is not in the radio frequency, so sadly it can't. But I thought to myself, if I had lots of money and this could be a radio frequency, I could buy the station, hire this person with a very deep voice, and have that person say, this is 109.5 FM, and discuss everything chemistry. And only the people who got chemistry will get that. Yeah. I said if. Okay. But yeah, anyway, this is how I remember 109.5 FM, and I've never forgotten it. It's not really, yeah, just a bond angle. Remember that. The shape of this molecule looks more like this. It looks like a tripod stand, like that. Tetrahedral, like that. Okay. And so it's not really the way it's drawn. And this one here, once again, nonpolar. Look at all the surrounding groups. They all look alike. There's no dots on the central atom. So go through this table and figure out, the different combinations. This one here is polar. Why is it polar? Not because the surrounding groups are different. They're all alike, but there's a lone pair right here. Same thing with this. 2 lone pairs is polar. So go through this right here and you see the different bond angles and how the names changes. So I'm going to go through this, the group of 4 real quick. And then I won't go through the rest of these, but they'll be available for you guys to look over. Okay. It goes all the way to group of 6. Okay, so let me finish up the group of 4. The group of 4, once again, you have 4 groups here, 3 surrounding groups, 1 lone pair. So you have here 4 surrounding groups, 3 are bonded groups, 1 is a lone pair. I stick with the perfect bond angles at 109.5 FM, right? This time the shape is called pyramidal. The shape has changed. Remember, the shape is formed by bonded groups. So we're missing 1 bonded group. So what they do here, they take the top of the tripod stand off. So this top part is taken off. And then once again, when I was learning this, I'm like, these names, they kind of sound wonky. It sounded like people were just playing around and they were coming up with these names and then it just stuck. So imagine if you take off this top part, right? Because it's not a lone pair, it's not a bond anymore, so it doesn't count for the shape. The bottom part, they say it looks like a pyramid, right? So some guys like, this kind of reminds me of a pyramid. Yeah, we can see that. It's a pyramid. We'll call it pyramid. And it's stuck. Trigonal pyramidal. And it's called pyramidal or trigonal pyramidal because it's a pyramid with a triangular base. Okay. Once again, I explained why it was polar. It has lone pair in the central atom. I'm going to end with this right here and go back to the lecture, right? So here we have Se with 2 hydrogens. Once again, we have 4 groups, 2 lone pairs, 2 atoms. That makes 4 groups, right? 2 of them are bonds, 2 are lone pairs. Bond angle 109.5. This is called bent. Wait, what? How do we get to bent? I'm going to draw all 4 groups and then remove 2 because remember, 2 of the groups are now lone pairs and not bonds. And in looking at the structure, we don't deal with the lone pairs. We only deal with bonds. So if I remove the 2 bonds out of the 4 that were available, what do I have left? That V. Remember I told you guys, when chemists have a V shape, they call that bent. So now we have 2 bents. We have a bent with the 3 group right here, and we have a bent with the 4 group right here. Okay, I'm not going to go into the 5 and the 6 group because we won't encounter that so much. Most of organic compounds not spend, but tend to have the geometry from the 2 group all the way to the 4 groups. I'm going to stop right there. Okay, once again, this one here will be in your notes for you to refer to. You can review this later on. You guys get the luxury of videos, man. Back in my days, I know, in my days, video, no. You're sitting there taking notes. You have like cramping hands and stuff like that. But you can see here, bond angle 120. I already talked about that. So you will go through, you draw your lowest structure. For this one here, your lowest structure looks something like this. It's going to be lone pairs here. Okay. And so 4 groups tetrahedral. So essentially when we go through the chart I just showed you, you can see how the chart goes with this. So remember how I showed you tetrahedral? Tetrahedral is when you have the 4 bonds like that. This is tetrahedral. And then of course, when you go from 4 groups where all of them are bonds into 3 groups where you have the lone pair. The lone pair is not, 4 groups where you have the lone pair. So 3 bonded groups and then 1 lone pair. The remaining shape we see here is trigonal pyramidal because it looks like a pyramid. Pyramidal, if I can spell and talk. Because it looks like a pyramid with a triangular base. And then, of course, I told you guys about removing, let's see, starting off from the left, removing 2 groups, right? And replacing the 2 groups with lone pairs. The remaining shape formed by the bonds only for this will be bent. Okay. Now, they gave you the specific bond angles, but it's okay to use 109.5 each time because it does get a little bit more complicated. So they have their own version of the table. Okay. This is a little bit more simplified. The one I gave you, though, it does a lot better job. Not that I'm competing with them or anything, but the one I gave you does a better job of showing you the Lewis structure so you can count the number of groups and make sure you're in the right category. Okay, so do feel free to use this, though. You're free to use that. You don't have to use, one versus the other. So, oh, look, we're kind of close to the end. I did talk about how to figure out if a whole compound or molecule is polar or not, right? Essentially, I kind of skipped some steps, but that's okay because I'm trying to make sure I finish this video today. Okay, we want to talk about electronegativity and bond polarity. So we're told here electronegativity is a measure of an atom's attraction for an electron in a bond. Remember when I told you guys earlier that there's certain atoms that are very small and they have a core that's very strong and positive, so it pulls electrons to itself? Yeah, we're referring to that atom. So in the periodic table, they have left out group 8 conveniently because group 8 doesn't really form bonds. We're now looking at fluorine. Fluorine is the tiniest atom that we have. And then rubidium tends to be the largest atom we have. I'm drawing this very large for exaggeration. So this is the largest atom. And then fluorine is the smallest atom. Okay, we're not comparing size. What we're comparing here is electronegativity. Because fluorine is the smallest atom, that also means fluorine has the strongest, or should I say highest nuclear charge. The highest nuclear charge. And the nuclear charge that's the positive charge that pulls electrons to itself. So because of that, I picture fluorine as a very petite element, a very tiny element whose core is so strong, it pulls all the electrons in the atom to itself, keeping the atom at a very, very, very small size. Every time we see fluorine, the atom is small. Okay? Because of that, fluorine not only pulls its electrons to itself, it's very small because it pulls electrons to itself in the core, it also pulls electrons from other elements. It's not personal. It's not like fluorine is very selfish, even though I went through school judging fluorine as being selfish. Okay? Fluorine has that behavior that it can't help because it has a very strong nuclear charge in its core. So it pulls its own electrons and pulls in any other electrons close to it. For that reason, chlorine has the number 4.0, which is the highest electronegativity. Oh, okay. It has the highest negativity. What does that mean? If fluorine is placed in a bond with another element and they're sharing electrons, fluorine is most likely going to pull the shared electrons to itself. Okay? So fluorine pulls with its strong core shared electrons to itself. So, like, come on, fluorine. We're supposed to be sharing shared electrons. Shares means that both people who are sharing or both elements have equal access to whatever is being shared, right? Not when you're in a relationship with fluorine, not when you're in a bond with fluorine. You know fluorine's behavior. So, fluorine will pull the shared electrons to itself so that from an outside point of view, it appears as though the electrons belong only to fluorine, but they technically belong to both elements. So that ability is called electronegativity. So here we're going to see if the electronegativities of two bonded atoms are equal or similar, the bond, now we're looking at bonds, not the molecule. The bond will be judged as nonpolar. Remember, nonpolar means non-different. This just means that the elements are alike, so they share perfectly. Here we have perfect sharing of electrons. They can't undo each other because they're literally each other. They're like identical twins sharing something. On the other hand here, oh no, what we have here is still a nonpolar bond where we don't have perfect sharing, but we still have sharing. If you look at the numbers on this table, hydrogen has electronegativity of 2.1, and then fluorine has 4.0. So you want to, sorry, does it say fluorine? I'm so stuck on fluorine. We're doing hydrogen and carbon. Hydrogen and carbon. So carbon has 2.5. Hydrogen has 2.1. So when you subtract these here, that's what they're getting the numbers from. The difference is 2.5 minus 2.1. And all we want to know is the difference. The difference here is 0.4. Here they all have the same electronegativity, 2.5 minus 2.5. The difference is 0. So there's a chart here that tells you the type of bond we're looking at. Oh, there's a chart. So if you have a difference in electronegativity of 0.5 or less, that bond is judged as nonpolar. And we can conclude electrons are being shared equally. If you have a difference in electronegativity of 0.5 to 1.9, that bond is judged as polar. Remember, polar means different. You literally selected two elements with different abilities, so polar. So when they bond, they will not bond the same way as the ones that are nonpolar. Electrons are unequally shared and they are pulled towards the element with the greater advantage. And the advantage here is the electronegative element. So for example, if you place hydrogen and fluorine, fluorine has the advantage. So fluorine will pull the electrons to itself because it's very tiny. Okay. And then if you have a difference in electronegativity of 1.9 and above, then you get the ionic bond. So the pulling was too strong that the bond broke, the relationship broke completely. And so electrons are being transferred from the less electronegative to the more electronegative element. So let's go back here and see. We said these are still nonpolar bond. They're sharing equally, supposedly based on that table, right? Let's see here. Oh, carbon and oxygen. Ooh. For carbon and oxygen, let's go back to the table and see. Carbon is 2.5, oxygen is 3.5. So we got 2.5, 3.5. Just take, we want the gap, right? Take the bigger number minus the smaller number, or take the absolute value so you always get a positive difference. The difference here is 1.0. Go to the chart to decide the kind of compound you have. Scroll down here. 1.0 is here. So the carbon-oxygen bond, this is a polar bond. They're not sharing equally. I want to talk about this symbol. The partial negative sign is given to the element that's more electronegative. So it's like not only are we judging oxygen as being more electronegative, we are labeling it electronegative. This one here is a less electronegative element. So they label all that stuff here. Okay. So once again, go ahead, go through this, take your time, take a pause, get up, walk away, come back, look at it. But yeah, so after we see all this, we're going back to where I was. Remember how I went over polarity of molecules and we saw that? So we're told here by the slides, the classification of a molecule as polar or nonpolar depends on the polarity of the individual bonds and the overall shape of the molecule. Here's where you go into that table, right? And you're looking for, do you have different surrounding elements, right? Or do you have lone pairs? If you have either one or these two scenarios here in the shape of your molecule, then you're dealing with polar molecule. And of course, each of the individual bonds in your molecule has to also be polar. Okay? So we're kind of wrapping this up by saying, in general, nonpolar molecules have no polar bonds. And then it says here individual dipoles cancel. This is actually a math term. If that makes sense to you, kudos, good for you. Most people, this doesn't make sense to them. So with nonpolar molecules, what we see here is the same surrounding elements like I showed you guys, and then no lone pairs on central atoms. Okay? With polar molecules, it says you at least have to have one polar bond. And then here, if this makes sense to you, this is great. Remember, with polar molecules, you have to have either different surrounding elements or at least one lone pair on central atom. Okay? And then real quick, we end here with the polarity of the molecules. So we're going to go through and look at the polarity of the molecule. So I'm not going to be looking at the polar bonds here, even though they say you can do that. I personally don't think it's a necessary step. I'm going to just compare the surrounding groups. Are they different? Are they alike? So I'm going to start with this first one here. One of these groups is not like the other, right? So by virtue of that, this is polar molecule. This one here, all the groups are exactly alike. And then there's no lone pairs, right? No lone pairs in the central atom. All the surrounding groups are exactly alike, so this is going to be nonpolar. For this one here, these surrounding groups are alike, but you have a lone pair, therefore polar, because you have one lone pair of electrons. This one here, you have no lone pair, but surrounding groups are different. These don't match that, polar. I like this method better just because if you have to understand dipoles to understand what they're doing and understand how vectors work and cancel out. So if you get that part, then that visual they're giving you right here will work for you, and you can always use that, right? But let's see. Oh, that's the end of the chapter. I'm so happy we got to the end. This is the first one, right? And so I'll be shooting the other one hopefully tomorrow. I don't know when. Yeah, and then posting that. But this is it for the first one.